Yeah, good morning to everyone. Let us start the session. We'll continue from the point that we started yesterday related to the virtual algorithm. Let's quickly recap what we did in transitive closure. The original relation that we will capture in one matrix representation, that is W. W stands for virtual, or it may also stand for the weight matrix. Okay. So basically, for every element belonging to that set, we need to identify is there any path. Suppose we want to update the weight I to j, so we need to identify the path, whether is there any path from I to k and then k to j. So we have to take, or means what, whatever is the result of this weight and the previous weight, what is the maximum that we will take in this, that is wij. That is, here we are discussing about 0 and 1, that is binary relation. So nothing like there are more than two values, either it will be 0 or it will be 1. If it is 1, it indicates, if wij equal to 1, it indicates there is a connection from I to j. If wij is equal to 0, that indicates there is no association from I to j. That's it. So what we will do without further delay, we'll take one example. But just try to understand, we are repeating this for every element, and we are starting with first row, and then we are starting with first column. So for first row, all the columns, we are going to update this. Then the second row, all the column, third row, all the column, nth row, all the columns. This we are finishing with respect to the first element. And then again, we are repeating for the next element. That way, we are computing this Warshaw's algorithm. Let's take a quick example. Let us take one example. We are having one set A, which is, just a minute. Set A is 1, 2, 3, 4. And you are having one relation R that is from set A is related to set A. You are having some relation R, okay? So that we are representing in terms of some matrix. Let us say this is your relation R. I'm just writing in terms of matrix. Unable to write the subscript superscript, so therefore I'll just write here matrix represented for R, that is equal to okay. So you are having 4 elements. Okay, so your elements are 1, 2, 3, 4. Okay, and there is some relation R. So I'm just writing that relation R, some random association. Let us say this is 1, 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 rest are 0. Okay. Okay. So what does it mean? 1 is related to 1, 1 is related to 4, 2 is related to 1, 2 is related to 2, 3 is related to 4, 4 is related to 4. So these are the elements that are belonging to your relation R. So just for your understanding, I'm just writing this, what are those elements in this relation. This is 1, 1. In another way, you are writing this relation, that is 1, 4, 2, 1, 2, 2, 3, 4, and 4, 4. These are the elements belonging to this given relation R. So what we are doing in Warshaw's algorithm, We are starting with this original given relation as W0, you call it. Okay. So W0 will be this you treat as W0, original matrix. And then your W1 that you are computing, that is your first iteration that you are starting. For every node, you are going to start this. So what we are doing in this process, we are just having this as it is controls. Let me just copy. Okay. Now what we are doing as per the algorithm, what is our algorithm? For k equal to 1 to n, do the following. So start with the first row, I equal to 1 to n. Okay, for first row, what exactly we are doing? For every column, 1 to n. So W11, 12, 13, 14, this is what we are going to compute in this iteration. So W11, that is equal to what? The previous W11 or WIK and WKJ. I will just write this for your understanding what exactly we are doing in each iteration. WIJ, that is equal to previous WIJ and where is or WIK and WKJ. That's it. So this is what is your the way you are updating the weight. So W1 right now you are starting with respect to this k is equal to 1. I will just write here ijk value for your reference. Okay. So I is 1, k is 1, I is 1, j is 1. So what exactly we are updating? W11 that is equal to previous W11 or W11 and W11. So W11 is already 1. So 1 or something is already 1. So there is no change in this. Then we are going for the next column, that is this. This is our focus. So what is this? W12 that is equal to previous W12 or W11 and WIK that is 11 and WKJ that is 12. 11 and 12 that is 0. So 0 or 0 something that is 0. So nothing is going to change. So there will not be any change. So again we are going for W13. W13 that is equal to previous W13 that is 0 and what is here WIK that is W11 that is 1 and WKJ that is 12 that is this. If you take the AND it is 0, so 0 or 0 it is 0, so no change. Similarly going ahead, what is this W14, K value is 4 now, sorry, J value is 4 now, J value is 4. So 1 4 that is equal to previous value that is already 1. So 1 or something is always remaining 1. So please try to understand. This is the way you have completed the inner for loop at present. That is j equal to 1 to m. So now it's time to go for next row. That is 2 to m. So that is 2. This will be set to 1. And again we will check. See, 1 or something it will remain as it is. 1 or something it will remain as it is. So you are just concentrating the places where there is a 0. There is no more changes for the 1. The 1 will remain 1 at itself. So you can quickly jump to the next. Already it is 0 now, so we need to concentrate here. So W23 that is equal to the J value is 3 now. W23 that is equal to previous W23 that is 0 or WIK that is 21. 21 is 1. Okay. And what is this? Uh, 21 is 1 and then KJ. KJ is what? 1, 3. So 1, 3. This is 0. 1 and 0 is what? 0. Okay. So basically what you are trying to do now for computing this W23, you are having which element right now into picture? 1. So you are checking the 2, 1 that is this and 1, 3 that is this. You are just taking AND operation 1 and 0, 0, nothing is going to. For example, if you want to do this, so this is intersection of these two columns, no? And our context is first element. So 2 comma 1 is 1 and 1 comma 4 is 1. So 1 and 1 is 1. 0 or 1 that is 1. So this is going to be updated now. This place is updated. Is it clear or not? Please let me know. Kindly quickly give the feedback in the chat box to understand whether what I'm doing right now, simulation, is you are able to understand or not. If any questions, please let me know. Quickly give the feedback in the chat box to understand. Okay. If any students who have not understood, please interrupt me and you can ask me anytime, because this is the basic fundamental thing you need to understand. On the basis of this, there are further algorithms. Right. So, in a quicker manner, if you want to do it in a quicker manner, how you will do this? Basically, what exactly you are doing in W1, you are having this element 1 into this K is there, which is intermediate node, basically. So you are trying to have all rows having something you want to find out all rows values, the association value means what? Suppose I want to find out this, what is the latest weight? That means what? I want to find out whether 3 is associated with 2 or not. So what exactly we are doing in this step? We are checking whether 3 is connected with 2 via 1 or not. 3 is not directly connected to 2, that's why it is 0. We just need to check whether 3 is connected to 2 via this k equal to 1. Okay, this element, via this element. So what exactly we are doing? We are checking 3 comma 1. That is what exactly here we are doing. I comma k. 3 comma 1 means this, and k comma j means what? 1 comma 2. So this and this, if they are 1, see what does it mean? Why we are checking this and this? 3 comma 1, if I write here, let me just write here what exactly we are doing. I's value is 3, j value is 2, and k value is 1. So what exactly we are trying to find out? 3 comma 2, whether they are related. If yes, then and then only we will check whether 2 comma 3 is also related. Sorry, k value is 1 here. 3 comma 2 is, we need to find out whether 3 comma 2 is related or not. They are not directly related as of now, that you are able to state. So what exactly we are checking? Whether they are related via 1 or not. So therefore, what exactly we are checking? Whether 3 comma 1 is related. If no, there is no question of checking 1 comma 3, because it is, if it is related, then we will check 1 comma 3. If it is related, then we will check, yeah, 1 comma 3 is also related. If 3 comma 1 is also related, 1 comma 3 is also related. Definitely 3 comma 1 comma 2. Definitely 3 comma 2 is related via 1. And that's why we will make it 1. Something like that. So this is what exactly we are doing in this Warshaw's algorithm. So you want to go in a quicker manner. This is a simulation. Means what exactly? You will finish all these rows by scanning this in this fashion, and then your k value will increment. Means you will check the next node, that is 2, into your picture. Means anything comma 2 and 2 comma something, and that way you will scan this entire matrix. Then you will take k equal to 3. then anything comma 3 and 3 comma something. You will scan this entire matrix. Then you will go for the next element. Anything comma 4 and 4 comma something. And you will scan this matrix and then you will stop. This is your last step. So I will go in a quicker manner to understand this. The simulation I have just shown for your understanding. So what exactly we are doing? Wait a minute. I'll just copy this here as it is again, just for your understanding. And I will just quickly show you what exactly we are doing. So what exactly we are doing now? What is something comma 1 and 1 comma something? Something comma 1. We will concentrate only on those nodes. Why? Because if no one is related to 1, why to scan that? See, you can see here. To update this, what is this? At present, let us say 1, 1, and this is 1. Okay, IJL is 2. So I want to check whether there is a relation from 1 to 2 via 1. So 1 to 2, there is no relation at all in the first length. Means W0 matrix is your first length. You are talking about distance 1. 1 is not related at all with 2. So 1 is related to 1 and 1 is not related to 2. 1 is related to 1 and 1 is not related to 2. So 1 and 0 is up to 0. So definitely your previous value will remain as it is. Okay. The point that I am highlighting here, what exactly we are doing, what is something comma 1 and 1 comma something. So in a quicker manner, efficient, see, Marshall algorithm will scan all these rows, means all the rows and column, all the cells. If you are having n by n matrix, what is the time complexity for this? If you are having n by n matrix, then it will have, suppose you are having n elements, so n by n matrix, n times you are scanning. So therefore n raised to 3. That many times you are having this computation. This is your time complexity. How you can speed up? You can also speed up this by this way. So basically, what is your objective to find out W1? What exactly we are doing in W1? What is something comma 1 that we will find out? And what is 1 comma something in first iteration I assume, for calculating of W1. So something comma 1 is what? Something comma 1 is what? We use 1 and 2. I will just write here 1 and 2. Okay. Yeah. And what is 1 comma something? 1 comma something is 1 and 4. 1 and 4. So what exactly we will do? We will just check something comma 1 and 1 comma something. 1 comma 1, is it already 1? So forget. 1 comma 4, if it is already 1, forget. 2 comma 1, is it already 1? Just forget. 2 comma 4 is not 1, so that you will make it 1. This is the way you can speed up the operation. And this is your updated value in this iteration. Your iteration is over. First iteration is over. No need to scan all these elements. You are directly identifying what is something comma 1. That is 1. That are related. What are some elements that are related to 1? Something comma 1 means what? What are those elements which are related to 1? These are listed here. What are those elements which are related from 1? That is 1 comma something that are related here. And you are just having all possible combination 1 comma 1, 1 comma 4, 2 comma 1, 2 comma 4. And we will just check whether 1 comma 1 is not associated, then we will make it associate. That's it. So this is your W1 matrix. For W2, that is your next iteration. Your previous iteration matrix will go as it is. Okay. Now here, this. Okay. Now here, our context is what is something comma 2 and 2 comma something. You are updating now. I okay. So can anybody tell me now what is something comma 2? Can anybody unmute and tell me quickly what is something comma 2 I should write? I missed one comment in the chat box. Viraj, Viraj, can you unmute? I just need to understand what is your doubt. Hello, Viraj.
Yes, sir.
Yeah,
Sir,
can you tell me?
sir, I understood after this point
You
only.
understand? Okay. Now you tell me, Viraj, what is something comma 2 from this?
Something comma 2. 2
Huh.
comma 2.
No, no, I just want elements. So should I write? Just like something comma 1
2.
we written. So something
2.
comma 2 is what? Who are related to only one element, that is 2. And what is 2 comma something?
So 2 comma 1.
1,
2 comma 4.
2 and
4. 4.
4. So 2 comma 1 they are already related, yes or no? Yeah, because
Yes,
2,
sir.
2 comma 1. Yeah, 2 comma 2 already related, yes or no?
Yes.
2 comma 4 already related, yes or no?
Yes, sir.
So no more changes. So W2 will remain as it is. Very good. So you remain unmute now. Wait for a moment. So we will go for W3. Means third element. We will take. The previous W2 will get copied as it is for W3. Okay. Now you tell me what is something comma 3 and 3 something in this. What is something comma 3 now?
Something comma 3. 3 comma. There is
Something
nothing with 3
3.
in second
So
place.
if there are no elements related to 3, we cannot check for 3 comma something also. So
Yes, sir.
W3. So we go for W4. Okay. So just a minute. Oh, sorry. Okay. So now here we are just checking what is something comma 4 and 4 comma something. So tell me what is something comma 4?
4 comma 4.
Something comma 4. Who are related to 4?
4. 4.
Only 4.
Yes, sir.
So one, two,
No,
three,
sir.
and four.
1, 2, 3,
Yeah.
4. All are
Yes.
related.
1, 2, 3, 4. Correct. And 4 comma something. What is that?
Only 4.
Okay, 4 comma something is only 4. So what we will do, we will check all possible combination. 1 comma 4 is already related, yes, no change. 2 comma 4 already related, no change. 3 comma 4 already related, no change. 4 comma 4 is already related. So there is no change. Okay. So by looking to this, you can see that no more changes are there because this is now transitive. You can check now what are those elements now by looking here 1 comma 1, 1 comma 4, 4 comma something, 1 comma 4 is already there. 1 comma 1, 2 comma 1, 1 comma 1 already there. 1 comma 1 is over, 1 comma 4, 1 comma 4 already over. 2 comma 1, 2 comma 4 is added. This is what we added now. Then 2 comma 2 is already done. 3 comma 4, 4 comma 4, 3 comma 4 is already there. So we have done. This is our Warshaw's algorithm. This is very simple example. So what I will do now, I will wait for your answer. Any question on this? Please let me know. Viraj, is it clear for you? Yeah, Viraj, is it clear now? IJK?
Yes, sir, clearly.
Okay, okay. So, remaining students, please let me know whether this concept is clear or not in the chat box. Quickly give the feedback. I'm just going through the chat box content to understand. If any doubts, please let me know. Okay, all right. If there are no doubts, let us quickly take one more example, which will do it by your own at present. Uh, Let me just have some matrix and then we'll start the work on that. Just a moment. Okay, let me take here. Okay, I am giving this exercise having five elements. Okay, can you quickly? I'm just dropping this as an exercise for you. You need to compute the transitive closure for this. So I will wait for 5 minutes and kindly do the exercise for this. So how many steps will be there? Initially W0 will be as it is. You will find out W1, W2, W3, W4, W5. W5 will be your, okay. W5 will be your last matrix. So kindly let me know now what is your answer from this final matrix. So I will wait for 5 minutes. You will just answer me in the chat box what are the new elements that you found which are not there in W0 at the end of W5. You will just text your message in the chat box what are those new elements. So I'm waiting for 5 minutes. Please complete this quickly. If any questions, any doubts, if you want to ask me, I'm open. Please ask me if any questions. I want the final matrix, W5. So if anyone have finished, please post your answer in the chat box. What are those new elements that you have discovered at the end of the final step? I'm waiting for the answer. Anyone finished? Please let me know. Okay, let us go step by step. What are the new elements that you have discovered in W1? Please post your answer in the chat box. What are those new elements that you have discovered in W1? Please do it fast. We need to proceed ahead. Okay, one answer I received from Rohini. That is 2 comma 3, 2 comma 4, and 5 comma 4. What about rest of the students? I think everyone is getting same thing. Very good, very good. Ritika, Chetan, Padak, very good. Hussein. So you are on track, very good. Now let me know about W2. What are those new elements that you are receiving in W2? What new elements you have discovered in W2? Okay, Hussein is saying 3 comma 1, 3 comma 3. Palak is also saying same. Rohini, Ritika, everyone is saying same. Very good, very good. That's good. Now let us proceed for W3. Any new elements in W3? Now let us discuss about W3. Any new elements about W3? What is W3 now? Any new element? 1 comma 2, 1 comma 5, and 5 comma 2. 1 comma 2, 1 comma 5, 5 comma 2. Very good. Now going for W4. Any new elements in W4? No new elements. Okay. And now finally W5. Any new elements in W5? Okay. In W5 also, no new elements. Okay. Very good. So at the end of W5, your task is done. Means you have received the transitive closure of the given relation R. The original relation R is not transitive. You have made forcefully this relation transitive by finding transitive closure. So whatever the new elements that you have discovered, the resultant W5 is your transitive closure of given relation R. That's it. So with this, we have finished up till now the transitive closure. Means we have finished everything. Means what is reflect all the properties like reflexive, irreflexive, not reflexive, then your symmetric, asymmetric, anti-symmetric, transitivity, and something like that. So let's quickly proceed ahead. Yeah, what is the application of this transitive closure? The application of this transitive closure is in terms of some a discovery of the association between two elements, maybe in terms of recursive database queries, maybe in terms of analysis of reachability, that is connectivity of transition graph in communication network. It is just like in your Facebook. You are receiving some notification. Do you know this person? So why you are receiving this notification? Because you are connected to some Y person, and Y may be connected to some another yes person, and that's why you may get a notification. Do you know this person or not? This is the application of the transitive closure in Facebook in terms of connectivity. Similarly, there is another application wherein to parse the automata theory that you are going to learn in the third year, to construction of parsing automata in compiler. So there also you need some transitivity. Okay. So with this, now we are going ahead to understand which relation we will call it as a equivalence relation. Basically, it is I can say it is a it is not a tie. It is basically a characteristics which is holding properties of multiple properties, and then we say this relation is equivalence relation. So basically, which properties if the relation is holding, then we will call this as equivalence. It is reflexive, symmetric, and transitive. If the relation is reflexive as well as symmetric and transitive, we call such relation as equivalence relation. And why we are interested for this equivalence relation? Because with the help of equivalence relation, we are able to partition the set of all elements into equivalence classes. Now, what is meaning of partition? Partition means what? We'll decompose given set into subset, such that if we take intersection operation of any subset, there will not be any common elements. The intersection operation will be always null. That is called as partition. Let us take some example. Let me just check. I'm just keeping this. Yeah. Let me come to the Okay. Uh, Let me tell you first of all what is partition. Let us say you are having set A. This I am writing in general. Okay. Set A. You are having some elements like P1. No, not P1. Let us say A1, comma A2, comma A3, comma dot dot dot, comma AN. Suppose n elements are having. Okay. Okay. So you may decompose this set into different partitions. At the max, how many partitions will be there? Can anybody tell me what is the maximum number of partitions we can have from this? Let me take a layman's example. We'll discuss first with instance. Let us say I have this set 1, comma 2, comma 3, comma 4. Let us say how many partitions? Partition means what? Decomposing original set into subsets. Okay. When we say this is partition, means this is having some partition like P1 is a subset. Wait a minute. There are some elements in P1. There are some elements in P2. P2 is another partition, something like that. Dot dot dot. So what I'm talking right now, what is first of all partition? If suppose you are having dot 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 P K number of partitions, the important properties of partition should hold. Number one, what are those properties? Partition is nothing but subset of the original set. So each partition is should have at least cardinality should have cardinality at least one. At least one. That means what? You cannot have a partition which is empty set. Okay. Number two, union of each partition, all partition of original set will result into original set. That means what? If I do the union operation like P1, union P2, union P3, union dot 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 dot, whatever that PK, what you will receive the original set, whatever the set A equal to. This is your property number two. And the third property is what? Intersection of any two partition is should be is always null. That means if you take any two partition Pi intersection Pj, it is always equal to null set. If these all three properties should satisfy, if you get, suppose when you are having this original set and you are partitioning into some k number of partitions, no, then this partition must hold this property. What is this property? Each partition should have cardinality at least one, means at least one element should be there in that partition. Union of all partition of original set will result into the original set, means if you unite all these partitions, you should get the original set. And intersection of any two partition is always null. You take any intersection between two partitions, there will not be any common element. Is this clear or not? Please quickly respond in the chat box so that I will proceed ahead. Kindly respond this in chat box. Is it clear or not? Yes or no? If any question, please let me know. If it is clear, mention yes. Otherwise, mention your question. I'm waiting for the feedback quickly. Up till now, only three students responded. What about the rest of the students? Gaurav, Chetan, Ruchika, Sahil, Neeraj, Viraj. I'm not able to understand for those students who are not responding in the chat box. Either you may have not understood at all, or you may not be present. This is one of the situation, maybe. Okay. So, if any questions, please let me know, because whatever topics that we are discussing, every topic is linked with some other topic. So, if you are missing one piece, you will going to miss the further change. So, don't lose anything. If any questions, please ask me at that point itself. Okay. So, let me now describe why I have introduced this partition concept to you. When a relation is equivalence relation, we are able to get the partition of the set. What is the beauty of this? We'll see the example. But before that, my question was here. Can you tell me what will be the maximum number of partitions that we can have for this set? Each partition is nothing but it is a subset. So my question is again I'm repeating. How many maximum possible partitions we can have which will satisfy these properties? Maximum number of partitions. How many? Okay. I received one answer from Viraj that is it is 4. So yes, the answer is right that we can have individual element as a partition. This is maximum number of partition answer. What is minimum number of partitions we can have? What is minimum number of partitions we can have? Maximum 4, that is true. That is you can have P1 that is 1, P2 that is 2, P3 that is 3, and P4 that is 4. This is maximum number of partitions. We satisfy this property. What is minimum number of partition we can have? Okay, so I received one answer from Hussein. So Hussein, can you just unmute and justify what is that partition that you are saying that is 1?
There should be one partition.
Hmm. Yeah, so what is that partition? What are the elements? Okay, that set itself is a single partition. That is 1, 2, 3, 4. Perfect. Very good. It is right answer. So what is this basically in terms of the data analysis? You can say you are trying to do, rather than classification, I can say clustering. You are trying to create the cluster. So this is a clustering application. See, equivalence relation will help you to identify the clusters of data. This is the beautiful application of equivalence relation. Now, we just discussed what is partition. We just need to understand what is equivalence relation. So, what exactly we need to do with respect to a relation R? Let me just open. Yeah. So, if we want to do the clustering, that means we want to find out the partition. What is our objective? Our objective is to make this relation equivalence relation. How to make this relation equivalence? You know very well that when the relation is equivalence relation, we satisfy three properties. It is reflexive, it is symmetric, and if it is transitive, then we say the relation is symmetric. Sorry, the relation is equivalence relation. So first of all, is this relation is equivalence relation? Okay, what I will do, I will just take one sample example of equivalence relation, which is by default. Uh, so that quickly I will just show you partition concept. Let me just identify the slide I made of it. I will not have it. Mhm. Just a minute. Yeah. So let us take one example of equivalence relation. Uh, and then we'll stop quickly. Let me just go through it. Okay, we'll take only 1, 2, 3, 4, and let us say you are having elements. Wait a minute, this is you copy. Okay, let us say you are having 1, comma 2, 1, comma 2, 2, comma 1, 2, comma 2, 3, comma 3, and 4, comma 4. So this relation is equivalence relation, which is satisfying reflexivity as well as symmetric as well as transitive property. So by looking to this, you can see this is forming one equivalence class. This is forming one equivalence class, and this is forming one equivalence class. So 1 and 2, they will go in one partition, 3 will go in another partition, 4 will go in another partition. This is in nutshell. We'll discuss in full length in our next session related to this. So in our next class, we are going to discuss about equivalence class, then followed by partial order relation, and then we will start with poset, that is partial order set. This is our agenda for the next session. We will stop here. Please post your attendance in the chat box. Thank you.